Welcome back again to Advanced Functions, MHF4U1. This is Exponential and Logarithmic Functions chapter. In this lesson number 3, we are going to evaluate logarithmic expressions and approximate the logarithm of a number to any base. First, we need to understand what is a natural logarithm. Now, from the previous lesson, we learned that if we have a logarithm with, let's say, 5, that means if you don't see a subscript, there is an invisible 10. So this is equal to log to the base of 10 to 5. So a logarithm to the base of 10 is called decimal, or we call it common logarithm. And this is what we just learned. Now, if we were to have a logarithm to the base of e, okay, now so you will see e on your calculator as well, and e is 2.71828. It's the same idea as pi being 3.14. It's same thing. E is equal to 2.718. Now, how do I get E? E is like a repercussion of the numbers starting with 1. So you're adding plus 1 over 1, plus 1 over 1 times 2, plus 1 over 1 times 2 times 3. And then you can approximate the next one, plus 1 over 1 times 2 times 3 times 4, and so on. Okay, so if we were to add this to the reciprocal of multiplication of increasing number, then you're going to get a number very close to 2.718. So if we were to have a logarithm of the base of e, and then let's say x, this is called a natural logarithm. And natural logarithm can be used in different language, so log to the base of e to x is equal to, so another symbol to represent natural logarithm is called ln x. So ln x, and ln, this symbol, we call it ln, like L-A-W-N. So please be familiar with the words, the expression common logarithm and natural logarithm. Okay. Now, when we are evaluating logarithms, there are 3 steps that I want you to consider. So it seems like there's 2 of the same one step. So first step is I want you to convert logarithmic form to an exponential form, which we learned in the previous sections. The base stays the same, okay, and the exponent becomes the output of the logarithm. Next, if the bases of both exponential expression are the same, then the exponents are going to be equal. So you can equate the exponent if the bases are the same. After, sometimes it can be represented in other form, which looks like this. Now, so this form, you could represent it this way. So for example, we have log base to the log b to y is equal to, so the base becomes a denominator and logarithm to the number becomes a numerator. So it looks like log, the big number goes at the top, numerator, log y over log b. So the base no longer becomes the base of log. The base is now 10 and 10. The reason why we're doing this is because we can now input the logarithm on our calculator. Because most calculator, when you see the log button, it's always base to 10. Okay, most calculators. But if you are able to input the base over here, x and y, let's say, so if you could change x, that means you have like a better calculator and you don't have to do this step. Okay. Question number 1. So evaluate. So evaluate means that you want to make sure your answer is a number. As always, you want to change the logarithmic form into exponential form. So it's going to be 2, the base is 2 to the y is equal to 8. Now, next we want to make it a same base. So obviously 8 is bigger, so let's change 8 as a base of 2, which is possible. 2 to the y is equal to 2 to the 3. Now you will notice that the base is the same, 2, 2. So we can equate the exponent, so y is equal to 3. Next, same thing, base is 5, so 5 to exponent of y is equal to square root 25. Then we understand that what's square root of 25? It's 5, so let's evaluate. And there's invisible 1 here, so y is equal to 1. Y is equal to log 4 to 1 over 16. Okay, so it's same thing. Now, I want you to always identify the base first, so 4 to the y is equal to 1 over 16. Recall that I want to change, because we are given fraction, let's make it into like a base, not a fraction. So we know that x to negative, let's say 1, or negative n, is equal to 1 over x to the n. So we could flip this fraction with a negative exponent, so 4 to the y is equal to 16 to the negative 1. But we understand that 16 could change into base of 4. So y to the 4 is equal to 4 squared negative 1, which is 4 to the negative 2. Therefore, y is equal to negative 2. Next, base is 1 over 3 to exponent of y. Now, because we're doing exponent, and then we have a fraction, I'm going to use a bracket. It's very important. Is equal to 81. Now, as you can see, 81 is a bigger number, so I'm going to change the fraction. So it's 3 to the negative y, so negative times y is negative y, equals, can I change 81 to a base of 3? So if you are not sure, you could use a calculator, so you can punch it in 3 to the 2, 3 to the 3, 3 to the 4, and see if you get 81. And you will notice that 3 to the 4 gives me 81. So therefore, the base is same. I'm going to equate it. Negative y is equal to 4. But we don't want negative in front of y, so let's divide it by negative 1, both sides. So y is equal to negative 4. Now, there are some special cases when we're evaluating logarithm. Now recall, for exponential, anything to an exponent of 0, we said it's 1. So therefore, logarithm of base of a to 1 is equal to 0, because a to an exponent of 0 is 1. Another is a to the 1 is just a. So when you have a same base with the number of logarithm, that means it's going to be equal to 1. So this is something that you have to understand. Another rule is we know that exponent and log are inverse. So therefore, if we were to have logarithm to the a with the same base, a to the exponent x, if you have a same base, is equal to x. Okay. Keep in mind, we just said the logarithm a to the a is equal to 1. So it essentially means it's 1 to the x, right? Because it's over here, 1x. So therefore, x can actually be brought, so the exponent of a logarithm can be brought to the front. So it's going to be x times 1, which is x. So again, another rule to remember is if I were to have log base of, let's say, b to the a x, I can bring the exponent of a logarithm to the front. So it becomes x times logarithm base to a. Okay, so therefore in this case, we have log a to the ax. I'm going to bring x to the front, the exponent. So it's x times log to the a, base of a to the a. But we know log a to a is going to be 1. So therefore, it's x. Next, another way is if you were to have a logarithm in an exponent with the same base, it's going to equal to x. Okay. Same idea. X, if you bring it to the front, it's going to be, because a to the log a is going to be 1. So therefore, x. So keep in mind, when you have a same base of a logarithm and the exponent, that number will be the answer. Okay, whatever it's equal to. So in this case, x and x here. This one, the last two, you must memorize the format. Memorize, for sure. Another second special cases is that we understand that expression log x is the common logarithm because there's invisible subscript of 10, and it can be evaluated using a log key on your calculator. So here are the steps. So most scientific calculators have a log key and ln key as well for natural logarithm. So again, ln is log to the e. So some scientific calculators have log, and do you see like two squares, one subscript and one big square or rectangle? And this is, you're lucky because you can put any base to the logarithm. So you don't have to do this step. Okay, but if you don't have this key over here, that means you would have to change it into common logarithm. So again, separate log x over log b, and then if it's a natural logarithm, or if I have log to the same base, then you can just change logarithm into ln, and you will still get the same answer. So we're going to try this. So let's practice using our calculator as well. So evaluate log 7, log to the base of 7 to 1 of 1. So if we don't see what we're evaluating, we could say is equal to x. That's what we're looking for. Again, let's put it in exponential form. So 7 to the x is equal to 1. We know that anything to an exponent of 0 is going to equal to 1, right? Because 7 can't be lowered to a base of 1. So x is equal to 0. Same thing, letter B is equal to x. So we say 3 to the x is equal to 27. 3 to the x is equal to 3 to the 3. So x is equal to 3. Another way you would like to do this by applying a special case is log to the 3. I can make 27 as a same base, 3 to the 3. So once you have a same base, the rule applies. The answer is 3 because same base of logarithm with the number is 1. So it's 1 of this expression, so it equals to 3. Okay, so this rule is coming from log a to the ax is equal to x. Okay, so you must memorize this. Okay, now evaluate, same thing. So you can use a calculator. You can just punch in log, and there's no a visible base, so meaning the base must be common base of 10. So on your calculator, you can press log, and you can press 0.001 and enter. Okay, and you will get your answer right away. But what if we did not want to use a calculator? Then let's change it into exponential form. 10 to the x is equal to 0.001. We know that 10 to the x, this 0.01, I could change it into exponent, which is 10 to the negative 3, right? 1, 2, 3. Therefore, x is equal to negative 3. Next, we have log to the c, so we're evaluating, so let's say it is equal to x. So 6x is equal to 50. Now, using your calculator, you will notice that 50 cannot be changed to any base of 6, because 6 is 36, doesn't work. 6 to the 3 is 216, so it doesn't work at all. Okay, so if that's the case, then we are going to change it into same base. So we could say logarithm. So we're going to attach log to both sides. So log 6x log 50. You can do that as long as you do to the left side, to the right side. Then I'm going to bring x to the front because that's where we're looking for x. Log 6 equals log 50. And then we're going to divide both sides by log 6. So x is equal to log 50 over log 6. In this case, you have to punch it in your calculator. So punch in log 50 divided by log 6. X is equal to approximately 2.18. Okay, so this is the calculator method where you cannot make the same base. Okay, next question. So we have a word problem here. Ian knows that a rumor spreads very quickly. He tells 3 people a rumor. By the end of next hour, each of these people has told 3 more people. Uh-oh. Each person who hears tells 3 more people in the next hour. Ian has written an algebraic model to represent the number of people who hear within the specific hour. N to t is a number of people told during the hour t, and t1 corresponds to the hour during which the first 3 people heard it and started telling others. So in which hour will 2,187 people hear the rumor? Okay, so this is like our everyday situation, and we can model this using logarithmic or exponential concept. So first, let's write down the formula equation. N to the t is equal to 3 to t plus 1. And we know that n to the t is number of people, and we want to figure out which hour, so we're looking for t. And we know that n to the t is, we're given 2187. So let's plug it in. So 2187 is equal to 3 to the t plus 1. Now, I wonder if I could change 2187 to a power of 3. So let's try. So 2 to the 5 is 243. Okay, it doesn't work. What about 2 to the 8? 6561. Okay, it's too big now. And then you will notice that, 3. 3 to 7 is equal to 2187. So it works. So if it works, I'm going to change it into 3 to the 7 equals 3t plus 1. Now that the base is same, I could equate the exponent. 7 is equal to t plus 1. T is equal to 7 minus 1, so it's 6. So that means at 6 hour, 2,187 people are going to know. Wow, that's a really short amount of time. Now, but let's say here's a scenario. What if we know that 2187 could not be changed into base of 3? So if that's the case, then, as always, you're going to attach logarithm. So let's attach log 3 to the 7 equals log 3t plus 1. Again, I'm going to bring exponent to the front. So it's 7 log to 3 is equal to t plus 1 log to the 3. And then, because we're looking for t, I'm going to move log 3 to the other side. So it's 7 log 3 over log 3, we're dividing, is equal to t plus 1. And you will notice that 7, so log 3 and log 3 cancels out, or you can punch it in your calculator, and you will still get 7t plus 1. T is equal to 6. And that's how you do it. So it's very easy if the number could be changed into same base, but if it's not, you can take the logarithm both sides and apply the logarithmic law.